now let's start with the next topic, so which is complex power and the reactive power. So by definition, if you take the complex power is nothing but the product of the RMS voltage phasor and the complex conjugate of current phasor. So if you just try to define it in terms of mathematical terms, so product of RMS voltage phasor, it means it is V phasor, and the current phasor is represented by I phasor, and this is complex conjugate, it means you can represent in terms of star. So you can represent simply that it is S bar equal to V phasor times I phasor star. So this is the definition of complex power. So from the given circuit we know, so you can calculate the impedance whenever you measure across its voltage V of t and the current flowing through the impedance. So generally whenever we mention impedance, it consists of both the resistive load and as well as the reactive load. So in terms of impedance, we just mentioned in terms of the real part which takes the resistive and the imaginary part which takes the reactive loads. Okay. So we know from the given thing, so what is V of t and what is I of t. So in terms of V phasor we can represent in terms of V RMS theta V, and in terms of I phasor we can represent in terms of I RMS into theta I, and in terms of complex conjugate you have to just change the angle sign, the sign of the angle, basically minus theta I. So from the given thing, so we can represent the complex power in terms of RMS. So basically it is V RMS times I RMS and the star, which indicates it as complex conjugate. And whenever you expand this form, you have this thing. So V RMS is represented by from the equation here, and similarly the I RMS is represented from this equation. So this one. So I RMS star is represented from this equation. So on the whole, whenever you have, again you have two parts. So S is represented, generally in previous thing we have represented S as the apparent power, where it is the combination of VRMS and IRMS. Since it is relating now VRMS and IRMS in terms of the complex conjugate, the phases of VRMS and IRMS in terms of complex conjugate, it is called as the complex power. So that is titled with bar. So whenever you have bar on top of the S, it means it is complex power. So in terms of complex power representation, so we have the same thing. So S bar is represented in terms of VRMS and IRMS by into theta V minus theta I. So where VRMS and IRMS is nothing but it is the apparent power, and this is the measure of your magnitude measured in VA. Okay. Okay. So we know this equation, the average power equation, the real power equation. So all this apparent power, the complex power, the reactive power, so everything which actually came, which is related with your real power. So whatever equation we solved in previous video or previous lecture, we have always taken the average power as our reference. So here also we have taken the average power for our reference. Okay. So the average power, the real power, generally it takes the real part of the power. So whenever you take, it takes only the real part. So you can see there is no complex term in it. Okay. So hence you can just modify this term in terms of real part, the real part of the entire average power. And you are representing this part, the power factor part, in terms of exponential form. So here whenever I am migrating, I am representing in terms of exponential form. So and I am just converting this VMIM because whenever we are measuring the power, basically whenever we are calculating the complex power or the apparent power, whatever it is, we generally take in terms of RMS. So hence I have just converted into RMS form over here, and which is representing my complex power. Okay. So here I am just mentioning this thing so that we already know from our explanation the complex power is nothing but the product of your VRMS phasor into IRMS phasor star. So IRMS conjugate. So whenever I just take and expand this form, so you have both the real part and as well as the complex part whenever you expand this particular thing. So real part we have mentioned, so similarly you have to mention for the complex part. So you can take this as an example to represent your complex form. So from the given picture we know the Z, the impedance, load impedance can be computed by this. So the ratio of your V phasor and I phasor is something but the impedance, and as well as we know what is your V phasor and I phasor, from where we know this is nothing but VRMS phasor and similarly IRMS phasor. That is the thing which we need to compute. So from here you can able to compute V phasor IRMS. So this is the thing which you can able to take from this particular equation and just substitute this thing. So this particular form VRMS in terms of this. So in your final equation where you substitute VRMS as Z into IRMS. So finally you get IRMS square. Okay. So IRMS square into Z. So where Z is now replaced with your actual circuit, which consists of both resistive and as well as the reactive load. So it is the real part and as well as the complex part of the circuit. So you are just representing that over here, and finally you are just calculating it inwards and you are finally computing the complex part equation. So where you have this part, which is real part, is generally termed in terms of resistive load since it is dealing with only the real part, and IRM square X is actually dealing with your reactive power. So hence we have related the reactive power from the final equation. Okay. So this is the final thing. So the energy exchange is happening between the source and the reactive of the load. So finally when you take here, so you have two things. So whenever you take the reactive thing, whenever your reactive power is 0, it means it's purely resistive. But whenever your reactive is basically greater than 0, it means it acts as an inductor. It means the power factor actually lags here. Whereas whenever your Q is less than 0, it means it acts as the capacitor and the power factor leads in this. It means the current is going to lead the voltage, and here the current is going to lag the voltage in terms of inductor. Okay, so I'm just concluding it once. So first thing you need to know, this is the circuit, and what is the complex part? It's a combination of your V phasor times I phasor conjugate, and we just compute all the parameters required for the V phasor and I phasor conjugate. So finally you convert it into exponential form and you compute the complex form, and you are going to relate this particular complex form with the complex form what you have in your actual circuit. So from there you just relate all these things and you compute your what is your real power and what is your reactive power. From the reactive power you have three observations, so three conditions, so three cases. When it is equal to 0, we know it is, so whenever it is equal to 0, it means it is purely real power. It means the real power exists only in the resistive load. So you can relate it. So that's how I am asking you to relate. And whenever your Q is greater than 0, then it means there is some phase difference which happens, because of which your inductor actually lags, where the current actually lags behind the voltage. Whereas in capacitor, the current actually leads the voltage. So this happens based upon these conditions. Okay. So this is the entire concept about the complex part and the reactive.